Okay, so today the goal is to talk about frame of reference and to understand how to convert mathematically between different different reference frames. So um, before I do that, again, let me just kind of regurgitate y'all's memory of that video that we watched a few weeks ago. Let me ask you guys a question. Right now, would you guys say that I'm moving? So right now, as I'm sitting in my chair here in my classroom, would you guys say that I'm moving? What do you guys think? Am I moving right now? Anyone? I'm sorry. So someone said no. Um, so um, so two people said no. Well, guys, uh, the answer to the question is not so obvious. Um, so as um, um, so as Anthony said, technically yes, in other ways no. Exactly, Anthony, you're right. So the question is, am I moving? Depends on what frame of reference are we talking about. It depends on motion. Depends on your reference frame, because motion is relative. So right now, if I were to ask you, am I moving relative to this room? You guys would say no. And if you say no, then you will be right. I am not moving relative to this room. But how about relative to the sun? Guys, am I moving relative to the sun? Anyone?
Yes.
Yes, I am moving relative to the sun. So when I switch to a different frame of reference, I am in motion, even though I am not in motion relative to this room. So the key thing is motion is relative. Whenever you are describing motion in physics mathematically, it is important that you specify a frame of reference. Um, and I'm going to play this video for you guys, just a few clips from the video. Um, Even though this video is old, it was made in 1960. I still think it's the best video out there for mathematically showing students how to convert between reference frames. Every physics teacher that I know uses this video whenever they're introducing frame of reference. So let me go ahead and make sure my sound is sharing. And then we're gonna watch a few clips from the video. We're not gonna watch the whole thing. The whole thing is 13 minutes long. We're gonna watch the beginning and then we're gonna watch the end. But if you want to watch the whole thing on your free time, the video is uploaded into Schoology for you guys. Well, the link to the video is uploaded into Schoology for you guys to be able to look at that on your own time.
We're used to seeing things from a particular point of view, that is, from a particular frame of reference. And things look different to us under different circumstances. At the moment, things look
You look peculiar. You're upside down.
no, you're the one that's upside down.
No, you're upside down.
No, I'm not. He's the one that's upside down, isn't he?
Well, let's toss for it.
All right.
Okay. You lose. He's the one that's really upside down. You better come into my frame of reference now.
My frame of reference was inverted from what it usually is. That view of things would be normal for me if I normally walked on my hands.
This represents a frame of reference. Just 3 rods stuck together so that each is at right angles to the other 2. Now I'm going to move in this direction. You see the frame at the same spot on your screen, but you know I'm moving this way because you see the wall moving this way behind me. But how do you know that I'm not standing still and the wall moving? It was the wall that was moving. Now the wall has disappeared, and you have no way of telling whether I am moving or not. But now you know that I'm moving. The point of this is that all motion is relative. In both cases, I was moving relative to the wall, and the wall was moving relative to me.
All motion is relative, but we tend to think of one thing as being fixed and the other thing as being moving. We usually think of the earth as fixed, and walls are usually fixed to the earth, so perhaps you were surprised the first time when it was the wall that was moving and not Dr. Hume. A frame of reference fixed to the earth is the most common frame of reference in which to observe the motion of other things.
This is the frame of reference that you're used to. The frame is fastened to the table. The table is bolted to the floor is anchored in the building, and the building is firmly attached to the earth. Of course, the reason for having 3 rods is the position of any object, such as this ball, can be specified using these 3 reference lines. This reference line points in the direction which we call up, which is a different direction here than it is on the other side of the earth. And these 2 reference lines specify a plane, which we call horizontal or level. In this film, we're going to look at the motion of objects in this earth frame of reference and in other frames of reference moving in different ways relative to the earth frame.
So I'm going to pause this right here, and I want to say something here. He mentioned that there are 3 lines here, and these 3 lines serve as our coordinate system, our frame of reference. Why did he use 3 lines? Guys, it turns out this is where we get our term 3 dimensions from. When we say that we live in 3 dimensions of space, what does that mean? Well, all that means is that I live in 3 perpendicular planes in space that are each perpendicular to each other. So we have a plane right here, we have a plane right here, and a plane right here. So we all live in 3 dimensions. And of course, we know we live in 3 dimensions of space because think about, guys, think about how I'm able to move in these 3 dimensions. So there's multiple ways I can move. I can either jump up and down, so I can jump up and down, or I can move left or right, or I can go forward or backwards, right? So I live in 3 dimensions because I can move in all 3 of those planes, okay? If you guys remember the old Super Mario game, the old Super Mario Brothers, the really old one, the original one that came out, whenever you guys are playing that game, you would say that Super Mario lives in 2 dimensions. He lives in 2 dimensions because, you know, whenever you're playing the game, you can only move, basically you can only move left and right, or you can jump up and down. So there's 2 dimensions, but obviously we live in 3 dimensions. So that's why in physics, whenever we're talking about a frame of reference, we use a 3-dimensional coordinate system to represent our frame of reference or our point of view, because we're measuring motion relative to this coordinate system. Okay, I'm gonna skip to the end of this video. The end of this video is actually the most important because here in this video, this is what you guys are going to need to understand to do your assignment for later on today. And the assignment involves converting between reference frames. Okay, so let's go ahead and play that now. And guys, can y'all hear the sound okay? Is it loud enough for you all?
Yes.
Okay, great. Thank you.
Now we're going to do another experiment on relative motion to show how to compare the velocity of an object in one frame of reference to its velocity in another frame of reference. If I give this dry ice puck a certain start, it moves straight across the table with a speed which is essentially constant because the forces of friction have been made
very small. This is just the law of inertia. An object moves with a constant velocity unless an unbalanced force acts on it. Now, will you give it the same start backwards?
I'll try.
If Dr. Hume gives it the same start, it moves back in this direction with the same velocity. Now, we are on a car here, a car which can move and which really is going to move in this direction, and we're going to repeat the experiment. All right, let's go. If we were making measurements here, then we would observe the same velocities, that is, the same experimental results that we did before. And so would you, because you are observing this experiment through a camera which is fastened to this cart. That is, you are in the moving frame of reference with us. But now we're going to do the experiment again, and this time you watch through a camera which is fixed in the Earth frame of reference. Now concentrate on watching the puck. Don't let your eye follow us. And I think you'll see that it'll move faster that way and not so fast this way, relative to you and relative to the wall behind. Here's the cart, which was moving along in this direction with a velocity u. We were sitting on the cart at a table. Here I am over on this side, and Dr. Hume was on this side, and we were pushing this puck back and forth on the table. When I pushed it, it went in this direction with a velocity v, and when Dr. Hume pushed it, it went in this direction with the same velocity v, but this is the velocity relative to the cart. What about the velocity relative to an observer on the ground in the fixed frame? Well, if it was pushed in this direction, its velocity is u plus v. If it's in this direction, its velocity is u minus v. This is all very reasonable. There's nothing very hard to understand here. The surprising thing about this expression is that it is not accurate in all circumstances. At very high speeds, and by high speeds I mean speeds close to the velocity of light, this expression breaks down. At these very high speeds, we have to use the ideas about relative motion developed by Albert Einstein in his special theory of relativity.
Okay, I'm gonna stop right there. For the sake of introductory physics, we're not going to be dealing with, high speeds close to the speed of light. That gets into more complicated scenarios. We're just going to be dealing with, very simple physics using this equation right here, because this is going to help us work out our problems for our assignment later on. That whenever you are converting between reference frames, all you do is just combine the object's velocities. So, for example, well, you know what? Before we do the example, I want to go back to the important part of the video because I want you guys to notice this here. This was the most important thing I want you guys to notice, is that remember when you were attached to the moving frame of reference and you looked at the cart moving in this direction versus the cart, I'm sorry, not the cart, but the puck. When you looked at the puck moving in this direction versus the puck moving in that direction, they appear to be going at the same speed, just in different directions. However, it was different when we switched frame of references. And so let's look at that now. I just want to be sure everybody gets that point, because that's the most important thing that you guys need to know in order to do your assignment later on. So, again, hold on. Let me go to the part where it's actually moving. Okay, yeah. So here's the part where it's actually moving. So notice if you look at the puck, look at the speed there, and look at the speed in this direction. So again, when you're moving with the object, you see something very different versus looking at the puck from another frame of reference, from a frame of reference that is stationary toward the Earth. And we're going to see that now. So we're going to look at we're going to look at the same situation, but now we're switching frame of references. We're no longer moving with the puck. Hold on. I'm waiting for it to start. Okay, there it is. So look at the speed now relative to, that back wall. And look how it appears to be going slower when it's moving in the opposite direction. So the point is, guys, depending on your frame of reference, the motion of objects may look different depending on your point of view. Okay. So with that said, let us do some mathematical examples. Okay, so working out a few examples. Okay, let us suppose here that we have an observer standing outside of this moving train. So this person in green here is standing on the earth, and he's in a fixed frame of reference with the earth. Okay, and this person is watching this train go by. Now let us assume there are two persons on the train. There's a person in red and there's a person in blue. Okay. Now, guys, let us imagine. Oh, sorry about that. Didn't mean switch sides. Let us imagine that the person in red has a ball in his hand. So this person in red, he's holding a ball. And he's about to get ready to throw the ball to the next person on the train. But let me ask you guys a question. Well, I tell you what, before I ask the question, let me label some velocities here on my diagram. Okay. Let us pretend that the person in green, from his point of view, he sees the train moving at 70 miles per hour in that direction. So he sees the train moving at 70 miles per hour toward the right. Okay. So he sees the train moving. I'm sorry, guys. I don't know why this is trying to switch colors. And it's not. Okay, let me get this right. Okay. So the person in green sees the train moving at 70 miles per hour to the right. Again, that's from the perspective of the person in green. The person in green sees the train moving at 70 miles per hour to the right. Now, let us go to the situation inside the train. Okay, from the point of view of the people inside the train, this person in red here decides to throw the ball to the person in blue. And as they throw the ball, from this person's point of view, again, from the point of view of the individuals inside the train, the ball moves at 5 miles per hour in this direction because this person throws the person in blue the ball so that he can catch it. Someone tell me, okay, if this ball is moving at 5 miles per hour from the point of view of the individuals inside the train, someone tell me from the observer outside the train, from his frame of reference, how fast is that ball moving? Someone give me an exact number. What do you guys think? Anyone? Yes, I see Courtney put in the chat. You're exactly right. So from the person outside the train, the person in green sees the ball moving at 75 miles per hour. You're exactly right. So you will combine this velocity with this velocity, so 70 plus 5, in order to get the speed of the ball from this person's point of view. And that makes sense, right? Because they're watching the ball travel on a moving train. And again, we're assuming that this is a train with clear walls, so the person in green can see inside the train. Okay, so the person in green will see that ball moving at 75 miles per hour. Now, let me ask you guys another question. Well, before I ask that question, let us consider this scenario here. Let's say the person in blue catches the ball. So the person in blue catches the ball. And as soon as the person in blue catches the ball, he decides to throw it back to the person in red. And again, from their point of view, the ball is moving at 5 miles per hour, but now it's moving in the opposite direction. It's moving toward the west. So it's moving toward the left, I should say. So, guys, someone tell me, if from the point of view of the people inside the train, from their perspective, this person sees this ball coming at him at 5 miles per hour. From the perspective of the individual outside the train, again, assuming these were clear walls, and he looked inside the train, from his perspective, how fast is that ball moving? Anyone? From the perspective of the person in green, from his frame of reference. Anyone? Yes, Courtney, you're right. So the person in green sees the ball moving at 65 miles per hour. So how do you do that? All you did was just combine the velocities, but here this velocity was negative because it was moving in the opposite direction. So 70 minus 5 gave you 65 miles per hour. Okay, so here's the key point that I want you guys to realize here. Notice how, depending on your frame of reference, you can get very different. You can observe things with very different points of views. The people inside the train, they see the ball moving at 5 miles per hour toward the left. Okay. However, the person outside the train, he sees the ball moving at 65 miles per hour toward the right. So depending on your frame of reference, not only can you disagree on how fast an object is moving, two observers can disagree on the direction an object is moving. Let us look at some more examples. These examples that we're about to do are going to look very similar to what you're going to see on your homework for later on today. Okay. So we have various situations here where a person is standing, where various individuals is standing on a train and they're running in different directions on the train. Okay, so guys, let us imagine that there's someone here outside the train. So they're standing on the earth. So there's someone here outside the train, and they're watching these trains go by. Okay, let us look at the situation. Let us look at situation A first. Okay, guys, let me tell you guys what these numbers mean. Basically, this number right here, 24 meters per second, that represents how fast the train is moving relative to this person, or in other words, relative to the ground. Okay. This this value right here, 8 meters per second, what does this mean? Basically, this represents the velocity of the person, how fast it's moving relative to the train itself. In other words, if you were inside the train, this person would be moving at 8 meters per second relative to the floor of the train, or relative to the platform of the train. So everybody got that? Okay, so someone tell me, if this person right here, if he's watching this train go by, and he sees this train moving at 24 meters per second to the right, and he sees the person, and the person on the train is moving at 8 meters per second relative to the floor of the train to the left. Someone tell me, from this person's perspective, how fast is this individual moving relative to him? Anyone? Yep, it's 16. It's 16 meters per second. You want to do 24 minus 8, which in this case gives you positive 16 meters per second. And here, labeling your positive and negative signs are important, as we're going to see in just a moment. Okay. So for your assignment, guys, later on today, whenever you guys are working your assignment, it asks you to label directions and also magnitudes of speeds. So basically, just so you guys know, anything moving toward the right, we say that's moving toward the east. And anything that's moving toward the left, we say that object is moving toward the west. Okay. Basically, any object that's moving toward the west, you want to give it a negative velocity, and any object that's moving toward the east, you want to assign it a positive velocity, and then you want to combine those velocities to convert to another frame of reference. Okay, so let us look at situation B here. Okay, so if we look at situation B, okay, so guys, from this person's point of view, they see this train traveling at 30 meters per second in that direction. Okay. Now, the person on the train, they're moving at 10 meters per second relative to the floor of the train itself. Okay, but they're moving in that direction. Okay, now remember what I said, guys. Anything that's moving toward the west, you want to label that a negative velocity. And anything that's moving toward the right, are moving toward the east, you want to label that a positive velocity. Okay. So someone tell me, when we combine these two velocities, how fast is the person moving on the train relative to this outside observer here? Can someone tell me in situation B? Anyone?
20 meters per
20 meters per second. You're right, Courtney, but is it a negative 20 or a positive 20? Sign matters here.
a negative 20.
It's a negative 20. You're exactly right. Because if you take negative 20 and you add it to positive 10, you get negative 20 meters per second. So, okay. So here's what this means. This means from this person's point of view, from their point of view, they see this person moving at 20 meters per second toward the west. That's what that negative means, toward the west. Okay. Let's do one more together. Let us look at situation C. So in situation C, this person outside the train, they see the train itself moving at 20 meters per second in that direction. Okay. Now, there's a person on the train. They're moving at 4 meters per second relative to the floor of the train itself. Okay, so they're moving toward the west relative to the floor of the train. Okay, so the question is, how fast is this person moving from the perspective of the outside observer? So what do they see from their frame of reference? Well, remember what I said, guys. Anything that's moving in this direction toward the east, we want to call that a positive velocity. And anything that's moving toward the west, we want to call that a negative velocity. Okay. So guys, when we combine those two velocities, what do we get there? Anyone? In situation C? What? Yep. So is it, Anthony, is it positive 16 or negative 16? It is positive 16 meters per second. Guys, it's important here that you label your sign. And again, when you guys are working on the assignment, obviously you understand why. So that means from the perspective of the person outside the train, from their frame of reference, they see this individual right here moving at 16 meters per second toward the east, right? Because that's what their positive tell us. They're moving toward the east. If you get a negative, that means they're moving toward the west. But if you get a positive, it means they're moving toward the east, relative to this person's perspective, relative to them. Okay? Any questions here? Any questions? Okay, as soon as this call ends, I'm going to post the assignment for you all as soon as we're done with the Zoom call. If there are no immediate questions for me, you guys are free to go. Have a good day.